Hi everyone! In this video we are going to go over another radical reaction called allylic bromination. So let's start by determining in the following molecule, where would we abstract a hydrogen? So this is cyclohexene. And let's figure out the most stable radical after hydrogen abstraction. So I'm going to draw in here 3 of the hydrogens. And I'm going to highlight them as different colors, but you can also label them A, B, and C if that's easier. I know not everyone has highlighters handy. Okay, and let's see what happens if we lose a yellow hydrogen, a blue hydrogen, and then a purple hydrogen. So what type of radical will we end up with, and which one would be most stable? So feel free to pause the video and try this on your own first, and then we'll go over it together. Okay, so let's also label our allylic and vinylic hydrogens. So the blue hydrogen is at the allylic position. So that is 1 carbon away from the double bond. And then the purple hydrogen is our vinylic hydrogen. So that's attached to one of the carbons on the double bond. Okay, so now let's see what happens if we lose a yellow hydrogen. So if we abstract that yellow hydrogen through a radical reaction, then we should end up with a single unpaired electron on the carbon that the yellow hydrogen was attached to. Okay, now what would happen if we lost the blue hydrogen? So if that was abstracted? Well, we would end up with a single unpaired electron on the carbon that was attached to the blue hydrogen, so the allylic hydrogen. And then what would happen if we lose the purple hydrogen? So similar process, we would abstract the purple hydrogen, and that would leave behind a single unpaired electron on carbon in the double bond at the vinylic position. Now, I didn't show the other 3 hydrogens on the bottom of the ring because they're exactly the same as the top 3 hydrogens. So it's just a mirror image, right? There's a plane of symmetry there. Okay, so which of these radicals is the most stable? So let's look at the radical after abstraction of the yellow hydrogen, so the top radical that we drew. Let's see, so that is a secondary radical, right? Okay, what type of radical is the next one down below? So that's also a secondary radical, but notice that it is next to a single bond, which is next to a double bond. So we can have a resonance structure here. So remember, we went over this in a previous lecture. This is very similar to carbocations. If you have your single unpaired electron next to a single bond, next to a double bond, so you have that sequence there, and I'll highlight that for you. So if you've got your unpaired electron next to a single bond, next to a double bond, then you can have a resonance structure. And remember, resonance structures are more stable than tertiary radicals. All right, so let's show the movement of electrons here. Okay, so the single electron can move down, and I'm using a fishhook arrow since we're only showing the movement of one electron. And then the pi bond can break apart, and one electron will join up with the radical electron to form a pi bond up above. The other electron will be left on the carbon down below. Okay, so now we've moved the double bond up, and there's a single unpaired electron down below. Now again, these are resonance structures, so we would actually see a hybrid structure. So resonance structures are just two different ways of drawing the same exact molecule. In reality, those electrons are delocalized across those two bonds. Just remember that. It's key. Okay, so we do have resonance here. Now let's look at the last radical after we abstract the purple hydrogen or the vanillic hydrogen. Do we have any resonance there? No, we can't really move that electron because it's right on the double bond, so there's really nowhere for it to go. And actually, let's go back to our first radical, the secondary radical. Does that have any resonance? No, we can't move that electron either. Okay, so which of these is the most stable? The one with the resonance structures. Oops, sorry, I hit my blank screen. All right, so let's write the blue hydrogen, which is also the allylic proton, is abstracted more easily or most easily due to resonance. And remember, if something has resonance, it is more stable. Okay, so now let's talk about allylic bromination. So let's say we start with that same molecule, cyclohexene, and we add Br2H nu, which is energy or light. So we would assume this is a radical reaction, right? And we would assume that a hydrogen would be abstracted at the allylic position. So I'll just highlight that. And because we would expect a radical electron to be left behind on that carbon, we then might expect a bromine to add to that position. So let's say it just adds right here. Now you could also have the enantiomer because bromine could add from above or below. However, if we run this experiment in real life, this is not the product that we end up with. So this is actually not observed in the lab. Okay, so what do we end up with instead? Well, what scientists find is if we perform this reaction, instead of ending up with the product that we expected, we actually end up performing just a simple halogenation reaction. So the two bromines will add across the double bond, similar to our addition reactions across alkenes. And then we also form the enantiomer. So what's interesting is that addition of Br2 outcompetes the radical addition. So most likely, the addition of Br2 across the double bond is just more energetically favorable. So we don't actually see allylic bromination when we use Br2 and light. Now, the reason for that as well is only a small amount of Br2 is turned into a radical. So how can we produce the allylic halogen? Because what if we do want to add a bromine to the allylic position? We can't do it this way because Br2 is just going to add across the double bond in a typical addition reaction. So there is a way to get that middle product there, that one that we don't observe experimentally using Br2. We're going to use an alternate reagent. So I'll draw this reagent for you so you can kind of see what it looks like. All right, and then there's a lone pair left on nitrogen. So this is called N-bromosuccinimide. And we just abbreviate that NBS. So if we use this reagent and add some light, so remember we would probably use a mercury lamp, we end up forming a bromine radical. So the bond between nitrogen and bromine is going to homolytically cleave. So we'll write here homolytic cleavage. And again, that's just due to the energy from the light that we're providing. And then we end up with two radicals. So nitrogen becomes a radical there. And then we also have a bromine radical. So what's great here is that we don't have any Br2, or we might have a little bit if two bromine radicals couple together, but this will limit the amount of Br2. So since we're limiting the amount of Br2 in solution, that will favor the formation of the allylic bromine. Okay, so what we could do instead, if we have cyclohexene and we want to add bromine to the allylic position, we would write NBS for N-bromosuccinimide, and underneath we could write HNu for light. And then we would get our allylic bromination, and we would also form the enantiomer. And this would form a racemic mixture because bromine could add to the top or the bottom, and that would be in equal proportions. So we have a 50-50 mixture of our enantiomers. Okay, so let's do a practice problem. All right, so I'm going to give you an alkene. And we're going to add NBS, so N-bromosuccinimide, and energy in the form of light. And I want you to write the full mechanism for this reaction. Now, because this is a radical reaction, remember to include the initiation step, the propagation steps, and then the termination steps at the end. Well, for termination, you only have to include one termination step, so you don't have to include all possible termination steps. All right, so feel free to pause the video, look through your notes, and see if you can write those 3 steps for this radical reaction. And then when you unpause the video, we'll go over it together. Okay, so let's start with the initiation step. So we already saw the initiation step on the last slide. So that involves N-bromosuccinimide going through homolytic cleavage. Okay, so we can show that bond homolytically cleaving to give us 2 radicals. Great. Easy enough. Now for the propagation steps. Okay, so remember the first step will be hydrogen abstraction. So let's look back at our starting material, so our starting alkene. Where would we abstract a hydrogen? Or what would give us the most stable radical? So remember, we just talked about allylic bromination. So we would abstract a hydrogen from an allylic position if it's available. Because remember, an allylic radical will give us resonance structures, which are very stabilizing. So let's redraw the starting material as well as our bromine radical. And we're going to, again, abstract a hydrogen from the allylic position. Okay, so our single electron from bromine is going to pair up with one of the electrons from the covalent bond between hydrogen and carbon. And then the other electron on that covalent bond will go to the allylic carbon. All right, so we end up forming HBr as one of our products, or one of our intermediates, I should say. And next we form our allylic radical. Okay, now remember there are resonance structures here, so let's draw our other resonance structure. Oh, I'm kind of running out of room, so let me just make this arrow smaller. There we go. All right, so let's show the resonance structure here. So remember that the reason we have a resonance structure is due to the double bond. So that pi bond is going to homolytically cleave, and we're going to form a double bond on the next bond over. So the single radical electron will team up with one of the pi bond electrons. the other pi bond electron will go to the carbon on the end of the molecule. Okay, now this resonance structure is not as stable because the radical electron, or the single unpaired electron, is on a primary carbon, right? So that's a primary radical. But remember, these are resonance structures, so the electrons are actually delocalized across those two bonds. Okay, so let's show what would happen when we add, let's see, Br2 to the top resonance structure. So earlier I said that we're limiting the amount of Br2, so this would be in trace amounts. So we're not going to see a lot of Br2 here, otherwise we would end up doing the addition reaction. Okay, so now I'm going to use blue arrows to show this next step. So the radical is going to form a bond with one of the bromine atoms. So Br2 is homolytically cleaving, and one electron will get left behind on the other bromine atom. So now we're going to form the following molecule. And remember, bromine can add from above or below. So I'm just going to draw bromine in a wedge and methyl in a dash. And remember, we're also going to form the enantiomer. Okay, so now let's show what would happen if we did the same thing to our bottom resonance structure. Okay. So where would the bromine add on our bottom resonance structure there? On the very end, right? Because that's where the lone electron is. Okay, so we would have a mixture of products. So let's draw all of these products up above. So let's draw our two enantiomers. And let's also draw that third product where bromine adds to the end of the molecule. Now, which products would be our major products and which ones would be our minor products? So if we look at the stability of our resonance structures, the top resonance structure is more stable because it's on a tertiary carbon, right? Our bottom resonance structure is a primary radical, so that's less stable. And we tend to favor the more energetically stable intermediates, right? So the two enantiomers would be our major products, and then the constitutional isomers, so the last product, that would be our minor product. And we would have a mixture, but luckily these two sets of products probably have different boiling points or different physical properties, so we would potentially be able to separate them. Okay, so now the last thing we need to do is write the termination step. And I'm a bit of a lazy chemist, so I'm just going to draw two bromine radicals coupling together. Easy peasy, that's our termination step, and I'll separate it from the rest here. Okay, So in this video, we went over allylic bromination. So if you do have the potential to form an allylic radical, then that will occur because resonance stabilized radicals are very stable. Well, I guess it's in the name, resonance stabilized, right? So those would be the major intermediates that would then go on to form our major products. And remember, bromine can add from above or below, so we would get enantiomers as our major products there. All right. Now, in the next video, we're going to talk about radical addition of HBr. So essentially hydrohalogenation, but with radicals. So I will see you then.